Now coming to the last of the subordinating topics, let's go over the subgroup variation. In most cases of comparison, we have factors with many levels. So it's not one composite sample that we end up studying, but a sample in a way divided into multiple levels of factors. This leads us to sample subgroups. In a composite sample, to understand the variance, we just need to consider how each observation differs from the overall sample mean. But in a subgroup scenario, we have to understand the variance within each subgroup. Also, since each subgroup is a part of the composite sample, we need to understand how the variance differs between these subgroups. Then only we can accurately determine the overall variance, which in turn is what we use in ANOVA. So let's see how it is done in practice. So we are comparing the mean performance of two or more samples or subgroups in ANOVA. Now ANOVA, what it does is to study the source of variation from a data point of view. The variance is coming from within subgroups, or there is significant variance between the subgroups. So that's the source. Either it's coming from within subgroup or between the subgroup. So it becomes important to know how much each component is contributing to the overall variance. Let's start with a brief introduction about each component to begin with. First is the natural variation in the process that leads to some differences in each data point, which is called common cause variation or the short-term variation, or what we say within subgroup variation. Second is when we note some abnormal or unexpected behavior in some of the samples or subgroups, which may have been caused by factors external to the process. Now this variation is called special cause variation or between subgroup variation. So both these components, that is within subgroup and between subgroup, when summed up, give us the overall variance when we are working with subgroups. Now that we understand these terms, we would be able to appreciate better when we say that in ANOVA we assume equal variances for sample subgroups. That is, we expect that within each sample subgroup, the variance behavior should be primarily due to common causes. And so it should be similar. Going by the same logic, the between subgroup variation should be greater than within subgroup variation. Then only we can have distinct and different subgroups. And then the ratio of between to within subgroup variation obviously would be greater than 1. Now to understand it better, let us take the example of, let's say, the ambulance response time in 3 cities. Here you can see the response time categorized for 3 cities in these 3 columns. Let's quickly go through the calculations to understand these terms of within and between subgroup variance better. Then it will always stay in our mind as to how these within and between subgroup variance are being arrived at. Now starting with the total within subgroup variance, it's given by total of sum of square of the city-wise average reporting time minus each data point for all the levels. That is, it is the difference between each data point and the mean for that subgroup. You square it, add it for all the levels, you get the total within subgroup variance. Statistically, you will see these values as sum of squares for factor in the ANOVA table. So from a calculation point of view, here we have the means for each subgroup. In these columns, each row is nothing but the square of the difference between the subgroup mean and individual observation. So this row is nothing but the difference between 13 and 12.66, that is 0.34, and then we have squared it to get this value. Then we sum up these columns to get the sum of squares for individual factor levels. And sum of these individual columns or factor levels for within variation will give us the total within subgroup variance. Then second, we come to the total between subgroup variance, which is given by the total of the square of the distance between overall mean and city wise or factor level wise mean multiplied by the subgroup size. Here in our example, each city has got 10 data points. That means the subgroup size is 10. And this term, the between subgroup variance, statistically it is called the sum of squares for error. So to calculate the between subgroup variance, first we need to find the overall mean, which is 15.7 in this case. And using the formula above, that is, let's say for city 1, square of the grand mean or the overall mean, which is 15.7, minus the subgroup mean, which is 13. So 15.7 minus 13, we take a square of that, multiply it with the subgroup size, which is 10, and we get 72.7. And adding the terms for all the three factor levels or cities, we get 128.6, which is the total between subgroup variance. And the overall variance for the sample, including these three subgroups, would be the sum of the total between and total within variance. That is 128.6 plus 24 will give us 152.6. And as a cross validation, we can check the ratio of between and within subgroup variance. So in this case, 128.6 is greater than 24. So the signal to noise ratio or the ratio between and within subgroup variance is obviously greater than 1. So the subgroups in this example are distinct and different from each other. I hope this video was useful. We would always be delighted to see your likes, comments and mails as we consider you an integral part of our learning endeavor. Keep watching this page as we plan to host more learning videos on concepts from DMAC, Lean, DFSS, Reengineering, Theory of Constraints, BPM and Operations Research. Please do subscribe to the page and keep receiving updates as and when we upload a new tutorial. Do share the links or channel details in your group so we end up creating a much larger learning community. In case you want us to talk about any specific concept, feel free to contact us. The contact details are mentioned here on the slide as well as on the page. So good luck and happy learning.